Hi, everybody. This is Carrie Worthington from the National Association of Regulatory Utility Commissioners, NARUC. On behalf of the National Council on Electricity Policy, we welcome you to the webinar on the impact of integrating renewable energy. We have a great session lined up today. We're so happy that you're able to join us. Before we get started, I wanted to just go over how to connect on the phones and some of the ways that we're going to be able to get your input for questions and comments. There is a three-step audio process, and it does include this audio pin situation. So some people just skip that step, so they end up having audio issues, but so please make sure that you enter your audio pin. Like I said, we're going to be taking questions from the audience. It will be after, we'll take one or two questions after each of the presentations, then we hope to have some time at the end for more in-depth conversation. You can send questions through either the question box or the chat function, and at any time during the webinar, please, if you have someone that you're asking it to, that you list that person, and if you want to remain anonymous, please indicate that as well. If for whatever reason you lose track of your chat boxes, you can always go to the view part of the bar at the top of your webinar screen and check it so that you can see the box. So welcome to the webinar. This is hosted by the National Council on Electricity Policy with a big help from the Eastern Interconnection Planning Collaborative. The National Council on Electricity Policy provides a forum for identifying, discussing, and debating the issues that underpin the revolution of the electricity generation, transmission, and distribution grid. NCEP is funded by the U.S. Department of Energy and is managed by NARUC. We're currently exploring the interface between the transmission and distribution systems as distributed energy resources gain access on the grid. Today you'll have 5 handouts on the webcast. So if you go to the handout section of the right-hand bar of your webinar, you'll see that the agenda and then the 4 presentations for today. We'll hear very briefly from Sonia Agrawal on the trends in renewable integration, and then we'll hear from 3 different perspectives from the RTO and ISO operators on what their situation is with integrating renewables on the grid. So I'd like to introduce Sonia Agrawal of Energy Innovation. She is the Vice President, and Energy Innovation is a policy and design and analysis firm. She leads America's Power Plan, where she and her team work with commissioners, RTOs, and other policymakers around the U.S. on how to design and implement policies that drive affordability, reliability, and cleaner energy. We've worked with Sonia in the past to develop the mega model game that explores utility regulatory models like performance-based regulation. So I'm really happy to be working with Sonia again, and I will pull up her presentation. And you should be seeing her presentation. Sonia, are you there?
I am here. Thank you so much, Carrie. It's great to be here with you all today. So I will just talk for a couple of minutes about trends that we're seeing out there in the field that have been evolving quickly over the last few years. As Carrie mentioned, we work with a lot of state public utility commissioners and commission staff on policy design, as well as in the wholesale markets on wholesale power market design. So I was delighted when Carrie reached out because I think this is a great topic and one that we work on quite a lot. So you can go on to the next one. So today I just wanted to, the next slide is a short agenda. It's very short. It's just about the way that the grid is transitioning, how quickly that's happening, some information about how the competitive landscape for power generation has flipped, and it's really a profound moment that we're in this country right now. And then the third, I'll just end with a few questions for for consideration, not to be answered immediately. So you can go on. The first slide here is just from EIA. It's data about the way that the electricity system has evolved since 1950. And I just think it's always helpful to step back and get a little bit of perspective. I think there's been quite a lot of rapid changes that have happened in the past few years that are quite fast compared with how our electricity system has been evolving in decades prior. You can keep going. And then the next slide has some information that the Advanced Energy Economy folks pulled together from FERC data. And it's looking at from this past summer through summer of 2021, what is on the docket for retirements at a national level at the wholesale scale, and what is on the docket for additions. And you can see it's a pretty stark transition happening here. We have a lot of coal retirements planned, a fair amount of nuclear, and then we're seeing a lot more solar and wind getting added to the grid. So that changes the characteristics of the grid, and you can't talk about renewable energy without in the same breath talking about flexibility options for the grid. So you can go on. The next slide is about how the competitive landscape has flipped, and that's really what's kind of underlying some of these overarching trends. You'll see here the comparison of new versus new costs. So this is levelized costs, looking at new wind and new solar compared with gas, coal, and nuclear. And you can see there's ranges here, but you can see part of the reason why you see so many wholesale level additions planned for the next 3 years is new versus new. You're seeing wind and solar and gas quite a lot cheaper than coal or nuclear. You can go on to the next one. The next one here is kind of what I think is one of the most profound things that's happening right now, which is just that this is looking at new versus existing costs. So you can see for wind and increasingly a little bit at least solar, you're starting to see wind actually be cheaper than continuing to run existing power plants of other types. So this is really unusual and disruptive in the electricity system. If you can replace capacity with a new type of technology that's actually cheaper than continuing to run existing technologies. So this isn't happening everywhere, but it is happening in an increasing number of places. And so this really, again, underscores why we are seeing the transition happening as rapidly as we are. And it also indicates that we might go through some periods of oversupply as we transition the system. So you can go on to the next one, Carrie. Thank you. So the last piece here is just giving a little bit of examples from a few different states. So Texas is the top wind market right now in the US, and it's also the fastest growing solar market, so lots of changes happening in Texas. Wyoming has recently proposed and is moving forward with a huge new wind farm. Iowa has 37% of its generation already from renewables, and it has an extremely reliable system. I'm not sure, Carrie, I think maybe we're on a bit of a delay here, but you can feel free to put all these ones up. And then there's just a couple of other examples here. Colorado, we've seen some just incredible solar plus storage costs coming in the most recent resource plan of the largest utility there, Xcel. Minnesota, Missouri. So we're just seeing across a lot of the middle of the country, especially huge shifts and huge new projects bringing a lot of renewables onto the grid. And then finally, just this last slide I'll leave with you guys. So the questions that emerge from these broader trends are to think about how to work with the ISO and RTO to manage these shifts, and that's precisely the topic of this webinar. So I think it's great to get the conversation started. Also, looking at utility plans to understand whether they are taking account of some of these really kind of crazy cost crossovers that we're seeing in the market. And then also that point on oversupply, we're probably in a bit of a period of oversupply in many of the markets, not as much Texas anymore. We've seen some retirements there, but just to think about proactively managing power plant retirements and what solutions are that might be available for communities. And then the final question here is one around flexibility. So thinking about how to plan for flexibility across the transmission distribution interface, which Carrie mentioned earlier, and also thinking about resources at the distribution scale from the point of view of state regulators that can help with flexibility all the way through to the overall integrated system. So those are a few questions, and with that, I'll just say thanks and turn it back over.
Thank you so much, Sonia. Next up, we have Dana Walters. He is a senior principal planner. He has over 40 years of experience in planning and planning management. He has worked for investor-owned utilities, a consulting firm, and with the New York ISO, where he is currently employed. I am going to be bringing up his slides. You should see your slides now, Dana. Are you there?
Yep. Okay, yeah, great. Good afternoon. Thank you for having me. I'll be talking to you about the challenges of integrating the renewable and distribution resources into the transmission planning. Next slide. Next. Can you hear me?
Yep, here. Yep.
Okay, there we go. Okay. As an introduction, the renewables and distribution resources cover a variety of types and sizes of resources that are connected on either the distribution or the bulk systems. So they're governed by different market rules, tariffs, and regulatory oversight. So there isn't a one-size-that-fits-all approach that we have to consider. As a result, we have to deal with the different possibilities differently in planning the transmission system. At NISO, the resources are connected to the bulk system that we study. We'll be studying for interconnecting them using a new streamlined study process that we have just submitted and approved through tariff changes. And those will be modeled as discrete resources at their point of interconnection. We use a class year process where we study a group of proposed facilities and identify the total potential impact, and then get a commitment from those who want to continue to pursue their proposals from there. And it's an iterative process that we have to go through. Resources connected to the distribution system are handled by the distribution providers. And there we're going to be modeling them as aggregated resources and modeling for planning studies. The planning processes were addressed by what I understand in a previous presentation to this group in 2016. And the next slide provides a high-level review of that process. So in the center at the top, we've got an annual NISO goal book, load and capacity data. And we prepare that so that everybody has the same information. It has our load forecast. It has information on the latest generators that are being connected and the status of what they're doing. We have included local transmission owner plans. And then all of that information as the baseline in that report is what's used for us to do our comprehensive system planning process. We have three basic perspectives that we look at, and you can see those in the next row down. Where we have public policy, which is a new process that we've implemented, and it's based on the FERC Order 1000. We have a reliability planning process and an economic planning process. So largely what we plan for are making sure that we have adequate resources, generating resources, And we're confirming that the facilities in the network are capable of serving the load over a broad range of conditions without damaging equipment. We have to also consider the system performance with regards to things like frequency and voltage and stability. So it's important that we have good data so we can model the system for all these studies. Next slide. As an overview, most of the renewable and distributed resources are wind and solar, and that's what most of the focus for everybody's on. But there can be other things as well. Most of the existing renewable resources that are connected to the bulk system in New York are proposed to connect to the bulk system, are located in the upstate New York area, as can be seen in the next slide, which we'll get to in a moment. In that the resources connected to the bulk system are following the existing interconnection and planning processes, this presentation is just focusing on the distribution energy resources. So what I'm going to touch on are the following after I show you the next couple of slides referring to the prior bullet. So what we're going to be talking about is what are DERs, DER type definitions, DER classifications, data requirements, visibility by the ISO and RTOs, forecasting load, system modeling security, interconnection processes, and measurement and verification. Next slide. Okay, so this is a slide that came out of our power trends, which we put out every year as well to try to give the markets an overview of things that are going on. And the point here is two things. One is to highlight how we break down the New York system. You can see all the A, B, C, E, D on the map. And those are zones that we use to study based on electrical or other characteristics of the regional areas. And we have something which I'll show on the next slide, which highlights just an overview of the transmission from a high-level perspective. But you can see that I'm referring to an upstate and downstate here, where zones A through E are classified as upstate and F through K are downstate. And in that table along the right there, you can see how all the existing, or not all, but most of the existing and proposed resources are upstate. And you can look at the map of New York, and it looks like a funnel, and that's basically what occurs. Is you've got New York City and Long Island down at the bottom there, and everything else gets funneled down through the system. So next slide, please. And because of that transfer, you can see where it's highlighted in yellow or gold type of color there, how the transmission facilities, and those are bulk system facilities, those are the areas that are most likely to get stressed with congestion. And that's between that upstate and downstate areas. And just make sure we're on the same page, congestion is something where the transmission may not be able to safely transmit all of the power all of the time. So when it's constrained, we have to redispatch the system. And when we redispatch the system, it's less optimal configuration, which means that it ends up costing more to operate the system. So it's an economic issue, not a reliability issue, as long as we have enough resources on the load side, in which case for us is the downstate side of that constraint. Okay, next slide. So getting into what are the DER resources, the definitions for DER can vary across the regions in the U.S. So it can make for a misunderstanding, and the practice can be more difficult because we don't have a common definition necessarily. The resources can be connected to either the wholesale bulk electric system or to the retail distribution system. Now, just you'll see the acronym later, so I'll highlight it, that the wholesale bulk electric system we refer to as the BES, and the retail distribution system we'll refer to as the non-BES. For DER that's connected to the distribution system, the DERs include resources that produce electricity and are not otherwise included in the formal definition by NERC of a BES facility. They're located within the boundary of any distribution provider and is a non-BES resource. Next slide. What I've got here is a lot of words, and I'm not going to try reading them all. I just wanted to highlight that there are these various definitions that we have to be concerned about. For distributed generation, that tends to be referring to non-BES generating units. For behind the meter stuff, it is focused on customer side of a retail meter that serve all or part of a customer's retail load with electric energy. Energy storage can have various types of facilities. Most people think of that as batteries, but we can also have things such as thermal storage, which can affect electrical usage. DER aggregation. One of the things that we'll have to be doing as a bulk power type of planning group is to aggregate DER, because we're not going to be modeling distribution facilities. It's too much for us to deal with, and we're not as familiar with those systems. But we'll be trying to aggregate common facilities at virtual points in the interconnection so that we can have a representation of what's available and how it's going to react. Microgrid system is an aggregation of DER, but it's a little bit different in that it has the capability of being balanced with load so that it can operate in an isolated or an islanded type of formation. And that's important because they have to still be able to maintain things like frequency and voltage when they're operating disconnected from the rest of the network like that. Cogeneration has been around for a long time, but that is another form of DER in that it has, potentially steam serving load, and it's a different type of load, and then it's a heat instead of electric, but it's still generated off of the same generators that we can use for electric generation. And then we have emergency standby systems, which are common for places that are very sensitive to having continuous power. Next slide. Next, there we go. In looking at this, we can group things as to a utility scale DER, which is predominantly the BES type of things that I was referring to, and a retail scale DER. And there is differences in how some of the data or treatment of those facilities will be handled as we go forward. So part of this is highlighting how complex and how things are cut and paste in different things because they have to be treated differently from different perspectives. But typically these are things that are in that up to 20 megawatt type of size because it's not economic to connect things that are too small directly to the transmission grid. And then the retail stuff will tend to be smaller in the distributed resources. And then the second bullet I sort of touched on already. So the next slide.
Dana, this is Carrie. Just because we have a few minutes left, do you want to skip to the interconnection process?
I wasn't done yet, but what do you mean by skip to it? I was going to try to keep going.
Okay, we just have about 2 minutes left before we have to move on to.
Oh, I'm almost that time? Okay, I see what you're saying. Okay. Yeah, the next couple slides I was going to try to push over faster anyway, because a lot of it I was just trying to highlight the differences and how we have to treat stuff. So let me go to slide 13 quick. I wanted to highlight that in some cases we have good data that we can meter. Other cases with behind the meter stuff we can't meter, and we have to have more estimate-based stuff, which makes it harder for planning, but it's part of what we have to do. Then I'm sort of referring to that in slide 15 as well. The ideal situation is we can meter everything, but in practicality we can't. Then the next couple slides I just have in there because I'm highlighting the complexity in the rules and practices And just wanted to have that available, and people can ask questions along that line, but we don't need to dwell on it. So if we go, which is my last slide, I wanted to highlight the fact that we'll do the best we can with modeling based on the information we have, with all the actual data that but what we're going to have to do, in that there's a lot of variables on all this, is we're going to have to get the best information we can from actual performance data and then cross-check our models against the actuals. We'll have to analyze situations where we've had problems on the system and see if we can model the disturbances and get things to match. Now, to the extent we have to estimate things, those estimates can have impacts. Just example with the hurricanes coming, it made me think about this. If we have a large dependency on solar panels and then we have a hurricane come in and wipes out a bunch of solar panels, we're not going to have information on what is available and what's not available. It's not like putting a new generator or putting a generator back online after you've had something come through. You can tell when it's fixed and when it's ready to go. We won't know how many solar arrays that we've lost and how quickly they'll be fixed. Not everybody will necessarily fix them. So that's going to be one of our challenges going forward. And because of this, we may have to have metering and communication equipment, which will be resisted by some of the DER type of people, but we are running blind if we can't get this type of communication and information for us to coordinate and develop our models. So I'll end with that, and we'll go to questions when people are ready. Thanks.
Thanks, Dana. Just due to the time, I think we're going to go straight to the presentation from ISO New England, Al McBride.
Sure.
Al is the Director of Transmission Study and Services at ISO New England. He's worked at the ISO for 12 years and is currently responsible for oversight of the interconnection standards. That's our presentation.
Good afternoon, everybody. Can you hear me okay, Carrie?
Yep.
Okay, great. So again, this is Al McBride from ISO New England. I have a few slides here. I'm going to go quickly through them, though, because there's one specific message in this presentation. I'll try and make sure that I get to that. So the key points are we've been adding a significant amount of distributed energy resources in the region, and we need to make sure that those are interconnecting in a way that doesn't affect bulk electric system reliability, which is our level of concern, I think, as Dana teed up quite well in his presentation. So I think we all know that there is the development of the new IEEE 1547 standard, which is a very positive development in identifying how these resources should be interconnecting, but because of the development timeline, won't be fully implemented until 2020. So really what I'm going to talk about is what interim steps we are taking before that standard is fully implemented. So next. So just very quickly about the ISO, we have three main functions. We operate the grid, coordinating and directing the flow of energy in real time. We design and run and oversee markets for the electric wholesale commodity, and we plan the power system to ensure its reliability over the next 10 years. Next. And so we're doing so for the 6 New England states, looking over the high voltage transmission system. We're connected, of course, to New Brunswick, Quebec, and New York. We make heavy use of those imports. We've been investing in our transmission system, and our all-time peak load is 28,000, a little bit over 28,000 megawatts. So next I'll transition to talking about the growth of DER in New England. So each year we have had to continue to increase our projections for how much DER is going to be added, making the impact a continuing continually increasing concern. The next slide has a depiction of that. You can see we've got our previous forecasts on here for how much would be added and our current forecast, and we've increased each year, heading towards a potential penetration of solar of something as much as 6,000 megawatts. We currently, of course, for 2018, we're a little bit over 3,000 megawatts, which you just saw our peak load. We're talking now quite a bit over 10% of our peak load being served by PV, distributed connected, and so that's obviously a fairly significant penetration. So on the next, then, so what that means for us is, and I have some planning engineering jargon here, but we need to test the bulk system and ensure that it's reliable. And included in those tests are subjecting the system to faults, which can include some fairly long duration faults. When those faults occur, they will lower the voltage on the transmission and distribution systems, and we need to make sure that resources are not tripping offline because of those low voltages. This was a key thing that was looked at in IEEE 1547. So the next slide. We're required to do this planning. We're required to know how much resources we could lose, and we're required to ensure that we don't lose too many resources, which could lead to cascading or other reliability issues. And if nothing else is done, we could be forced into the situation of some type of system upgrade. So that's the bulk level concern, is without the ability to ride through for these types of disturbances, we could be losing too many resources. So next, we summarize where we are with IEEE 1547 and the associated Underwriters Laboratory Standard. So I think, as most people know, it has been around for a few years, was amended in 2014, and then a significant revision was undertaken recently over the past couple of years. And the last revision has completed the rebalancing process. And the next slide. So the question is then, so that's great, the new standard is approved, but it turns out there are a number of more steps before the standard is in effect fully implemented and implementable. An associated testing standard has to be developed and approved, and then the Underwriter Laboratory Testing Standard number 1741, which complements 1547, has to be updated for the new standard. And so you saw the trajectory of how much we are adding and have added of distributed energy resources. So we felt that we couldn't wait until 2020, when everything is fully implemented, before addressing things like the ride-through issue that we believe is needed on the distributed resources. So next, then, we went to looking at what is out there and what we could make use of. And in California, to support Rule 21, there is a Underwriters Laboratory Standard 1741 SA, which does measure and test and approve the ability of inverters that have the ride-through capability that we need. So then we went to developing next an interim solution. On the next slide. So to get the performance that we believed we needed right away, or for all resources going forward, we identified a group in Massachusetts, which is our largest state, largest load, and has the most distributed energy resources being added at this time. They have a group there called the Technical Standards Review Group, which is a group that convenes distribution utilities, developers, manufacturers, and the state regulator. And it turned out to be an ideal group for discussing the issue. So next, we discussed the various aspects of the problem: transmission and distribution, reliability and protection, having the ability to ride through, and allowing time for manufacturers to respond. So an approach was discussed and agreed upon at the review group and captured in what we've called a source requirements document, which we've issued and which can be used by the underwriters laboratory to certify equipment. And on the next slide, this just quickly gets to what we've put in place, and this is somewhat technical, but we've identified that going forward, distributed energy resources connected to the distribution system have to have these ride-through capabilities. OV is short for overvoltage, UV is short for undervoltage. So for example, in the UV1 row, an inverter would need to remain connected to its interconnection if the voltage is 0.88 for 2 seconds. So, and the other parameters are there. That's the technical requirement. This lines up with 1547, and we might be updating it also to complement the NERC ride-through standard, which is NERC PRC-0224. The next slide covers the frequency settings. These are similar. So going forward, these resources will have the ability to ride through these frequency disturbances described here. The next slide describes the timeline. So for the most part, we're still working on Vermont and our municipals, but in Connecticut, Maine, Massachusetts, New Hampshire, and Rhode Island, all of the PV installations, solar PV installations that are going to be installed will have the ride-through requirements that I described, and so address our concern of not losing too many resources or more resources than we expect in the case of a voltage or frequency disturbance on the system. I'll just briefly touch on next steps. We're going to continue to work with utilities on implementing the standards, and those that haven't yet fully adopted it. And we're also continuing to work on adopting advanced inverter functions when the 1547 is fully implemented on the timeline that I described. So the message is that we identified at a bulk level the reliability problem, that the industry is headed in the direction of having equipment that performs as necessary, and we were able to work in the region with our stakeholders to identify a set of requirements that meet our needs while we're waiting for full implementation. That's it, Kerry. That's everything that I had.
Thank you so much, Alan. I don't think that we have any questions for you at this time, so I believe we're going to go to Jordan from the Mid-Continent ISO. He is the manager of policy studies there, and we'll circle back once he's finished with some questions that we've received. Let me just pull up your presentation and we can get started.
Good afternoon. Can you hear me?
Yes, we can hear you.
Great. So as the presentation is getting pulled up, again, my name is Jordan Bakke, and I'm here to represent a little bit different topic than the other speakers talked about, and that's a work effort that we have ongoing in MISO to understand the impacts of high levels or increasing levels of renewables over the long term within our footprint. So MISO is the ISO in the middle of the country, the Mid-Continent area, stretching from Hudson Bay down to the Gulf of Mexico. And we are in a position of a very wind-rich region of the country, but also a region that has relatively decent solar resources as well. And this work effort is to explore the impacts of growing levels of those resources. So can you move on to the next slide? Again, over the last 10 years, we went from a position of having almost no renewables, no wind and solar on our footprint, to where we're at now with about 20 gigawatts of primarily wind, but with a growing level of solar penetration. We've taken several actions over that time frame to increase the visibility and control of these resources, as well as improvements on transmission deliverability and forecasting that has enabled the deployment of this about 8% on an energy basis, or 20 gigawatts of renewable energy within the footprint. But the work that we have ongoing here is to ask the question around what is next. What actions are needed? What consequences are we likely to see of increasing levels of renewables above and beyond what we see today, and what's in the generation interconnection queue, which is what's forecasted here for the next 3 years on this chart. We've heard earlier about the drivers of renewable growth, and so I won't go into that at this moment. Next slide. So the quick overview of the study, or what we're looking at here, we're looking for what we're calling inflection points. So points in time where a significant change will be needed in either the operations or the infrastructure of the system in order to deliver these increasing amounts of renewable energy. So what are these big things that we'll need to focus on from a grid perspective as time goes forward? And we're doing this through 3 specific focus areas. One is resource adequacy, so the ability to have the capacity that you need at all the given hours of the year. The second one, energy adequacy, the ability to continuously operate the system from 1 hour to the next. And then operating reliability, the ability of the system to withstand an event or a contingency and remain stable because of that, and within all of our operating security limits. So we're looking at a spot where we're at now around 8% renewable penetration, up to increasing and significantly increasing levels going forward, and understanding what that means to the system. Next slide. So let's see. This is supposed to be a video. We'll see if it plays. Can you try to click on the bottom? Oh, there it goes. So this is just a brief overview of the resources that we're looking at and modeling within the system. So green being wind, yellow being utility scale solar, and the black dots distributed solar, and looking at the deployment. So we're primarily wind in the north region of MISO and primarily solar in the southern region, and a mix of other resources around the country. And so this is just to give a flavor of what is going into our models as we are exploring the questions which I detailed in the previous slide. Next slide, please. So while this is hopefully coming up, one of the first things that we looked at is essentially the resource adequacy implications. And what we've found so far is that even in a system like MISO that is dominated by wind in both current and in our forecasted projections, you still see the large impacts of solar generation, and this effect where you are shifting the primary risk away from your peak load conditions in the year to the time when the sun is setting in the evening. And so this chart shows the load net renewable curves and the risk or the probability of losing load on the bottom. And we find that the acuteness and the timing of that loss of load event is shifting, like I said, into these evening hours as the sun is setting. And we found that wind is helpful in preventing some of these things, but it is not a panacea of this risk shift event that we're starting to see or forecast going into the future. Next slide. And so this is a quick demonstration of the seasonality and the performance of our modeled wind and solar generation within the footprint under increasing levels of renewable penetration. And you see that solar is very correlated with each other, which is causing this risk increase over certain hours of the day, the morning and the evening, but especially the evening. And that we find that wind, it drops off in the middle of the day and starts to ramp up at night, but they're not perfectly correlated with each other, balanced. And so it creates this additional need for other resources in the system, even as you increase the level of renewables. Next slide. So we did a variety of sensitivities and asked questions around how can we improve some of these things that we're seeing. And so this is looking at the ELCC or the ability of renewables or any technology to support load over the year. And we find that wind positively benefits solar and solar positively benefits wind when they're deployed together. And it doesn't have to be at the same location, it just has to be within a connected region like MISO. And so they are balancing each other or helping each other and improving the overall picture, but it has diminishing impacts or effects as penetration increases. Next slide. So similarly, we looked at the geographic diversity. So the more you can spread your resources around to capture the weather variation, we see positive benefits of that type of diversity as well. And so the ability of both the technology and geographic diversity to improve the outlook or improve the ability or the performance of the renewable fleet going forward is there, but it again has somewhat limited ability to support that. Next slide. So moving on to a different area, which we're calling operating reliability or energy adequacy, and looking at the energy performance of these resources. We see that we have in kind of an obviously decreasing level of coal and gas generation on the footprint as being supplanted by the increasing levels of wind and solar, with a consequential reduction in emissions. And on the right, we see that we have an increasing level of total capacity on the system because the renewable resources that are coming online have a high install capacity, but a diminishing ability to support the capacity needs of the system. Next slide. A few other findings that we've got so far is a changing of ramping patterns as renewables increase. So similar to the findings we talked about earlier, small amounts of solar can have large impacts on the system, even if you're wind dominated like MISO. And so you start to see these ramping behavior changes of the thermal fleet, where it needs to ramp up in the morning, then down in the afternoon, or in the late morning, and then up again in the evening, and down again. And so there's a lot more variation that we're likely to see going forward as this deployment continues. Next slide. So changing over to more of a transmission focus, and some of what we're finding is that the stressful points, the points that we need to study in order to maintain system reliability, are also shifting. What we've seen in the past is that the dispatch assumptions or the level of similarity around these critical loading conditions are consistent or similar in the past. So at peak load, you're likely to see your coal, nuclear, gas generation running at near maximum. But as renewables increase, the variety or the variability of your dispatch assumptions and patterns continually change as you operate around these critical points. And what we see here is you could have a situation where you have high levels of renewables and lower levels of thermal dispatch, or vice versa, surrounding very similar loading conditions on the system. So the complexity and the focus of study going forward also needs to incorporate that increased variability from a transmission planning perspective. Next slide. This is an attempt to show what those operating conditions look like over a specific day. And one of the patterns that we're starting to see emerge is the direction and the amounts of energy flows are changing quite a bit as penetration increases. So today we have, relatively lower amounts of long distance energy flow, as well as the directionality of that energy flow. But as renewable penetration increases, those two things start to reverse. So we see magnified flows at certain times of the day, and then that can diminish at other times of the day. So the ability of the system to be flexible, to incorporate that both from a transmission and a resource perspective, will become more important as we move forward. Next slide. Looking at the complexity of essentially thermal and voltage violations from a reliability transmission perspective, we see that the complexity or the amount of upgrades that would be needed are most concentrated around the locations of this renewable deployment, but it really gets to be spread out throughout the footprint. And so one of the overall objectives of this work effort is to understand the complexity of the integration and use that for other more base business work to determine exactly what would be needed as we move forward. And so what we found so far is that at lower levels of penetration, even up to 20%, the overall complexity of the challenge is pretty simple. You can use standard business practices and engineering practices to solve the integration challenges that we're seeing. And next slide. So the one thing that I didn't really touch on because of the time that we have here is we're also exploring some stability or dynamic stability impacts such as frequency response performance and voltage stability performance of the system. We can discuss that more later, and on the last slide I have a link to additional material. But as a recap to what we're seeing so far out of our study, and this is preliminary or interim findings at this point, we're still working through this effort, is one, the risk of losing load compresses into those evening hours and shifts more acutely into that sundown period of the day. And as a result of the shift, the available energy from wind and solar resources during those hours decrease. But on the positive side, the diversity of the different technologies and the geographic distribution helps improve that ability of the renewable fleet to meet load. We're seeing that the direction of ramping will continually change, so the variability in the direction of the overall fleet to ramp to meet those needs will increase. And then under the assumptions so far through 20%, which is about where we're at now within the overall study, the complexity of the integration challenge is relatively mild. And with that, that's my last slide. We can move on to questions. And like I mentioned, there's a link here to additional material. We have some recorded webinars that we've done for this work. If you want a long form presentation or a deep dive into the assumptions behind it and some additional results, and you can find more information at that page on the overall work effort. Thank you.
Wonderful. Thank you so much, Jordan. We're going to open up to questions right now. So we've heard from the New York ISO on the complexity of forecasting and modeling and the treatment of DERs. We heard from ISO New England on the interconnection standards and the reliability problems that are associated with them. And finally, from MISO, we heard about the impact of renewable integration at variable levels. I do believe we have questions. Danielle, are you there to relay them?
Absolutely. Thanks so much to all of our presenters. For Dana, we got a couple of questions for the New York ISO. Then I think these are mostly captured in how are you modeling non-wires alternatives within your planning processes? One specific question was, what happens if you see both generation and storage installed at the same location on the grid? Is that something that you all are modeling at this point? How are you treating either current or anticipated non-wires alternatives such as storage or aggregated distributed energy resources?
Okay. The storage is not something we have a lot of yet, so I wouldn't say that we're actually modeling it yet. But what we're going to be doing is we're going to be trying to model things in a homogeneous way, so that if we have solar in storage, we'll be trying to model the storage capability separate from the solar capability, even if they're at the same location, because they'll be operating differently in different time frames. And it also depends upon the type of study that we're doing. If we're doing a power flow study, we'll probably look at it more from a sensitivity perspective. If we're doing a resource adequacy type of study, we'll be looking at things with a probabilistic perspective. So we can model that aggregated resource with the appropriate type of characteristics at the appropriate location the best we can.
Great, thank you so much. And then, Carrie, we also got a question, or a couple of questions for Jordan, if you're still there. The first of those was in a similar vein, but the questioner says, some researchers are suggesting that flexible loads can help manage the variable outputs from integrating renewables by turning on and off when it's beneficial to the grid. Are we starting to see any modeling capability to help analyze those opportunities?
Yeah, that's absolutely
directed
the case.
At Jordan, but then maybe.
Yeah, that's absolutely the case, and it's something I skipped over in the short time that I had to talk about this. And we do see a lot of benefits for flexible load, whether you want to call storage flexible load or demand response energy efficiency type programs, any types of controllable load to mitigate that risk period, especially caused by the ramping on the solar generation, can have very positive benefits to some of the trends that we're seeing. Modeling wise, it's a kind of a difficult question. There are some tools that we use internally, as well as some companies that we consult with do use to model that in essentially a capacity expansion type paradigm, to look at the ability or the benefits of adding load control versus the benefits of other types of resources that would be needed to meet your load throughout the year.
Excellent. That's great to hear. And then I think we probably have time for one more question that came through. This was directed to everyone. Are any of the RTOs starting to model what would happen if we as a country started to develop offshore resources in the Atlantic or the Great Lakes, presumably offshore wind specifically? Is that on anyone's radar screen as a potential future resource in your planning?
This is Dana. I can respond to that. We do have active interest in doing offshore off of Long Island, and we have been working with NYSERDA in evaluating some of those options and providing information to developers. But that's similar to modeling any other generating resource. You have to have a resource and modeling characteristics for the resource and a point of connection.
Yeah, and this is Al McBride from ISO New England. We also have several proposals to add offshore resources in our interconnection queue, and our states have been sponsoring requests for proposals to result in power purchase agreements with some of those resources. So we have projects that are moving forward here, and we'll be integrating them and going through some of the items that were kind of discussed today, the different levels of integrating them from a performance and forecasting perspective as they complement our operations and reliability.
And just to round it out, this is Jordan. There has been some limited talk about offshore in the Great Lakes in MISO, but we're in a bit different situation in that we have high quality, low cost areas onshore that are relatively nearby to the Great Lakes that make the economic viability of any type of offshore wind much worse than it would be in other parts of the country.
Wonderful, thank you all. I will just say we got a few more specific questions on particular slides. I will forward those along to the presenters and ask that they respond directly to the folks who are asking them, and we'll handle those offline. That's all we have for other questions, Carrie.
Thank you so much. And for the audience's purposes, that was Danielle Saspernet. She's the director of the Center for Partnerships and Innovation at NARUC. And we'd like to close the webinar at this time. It's 2 o'clock on the dot. I want to give a really big thank you to Dave Whiteley at the Eastern Interconnection Planning Collaborative for hooking us up with these awesome presentations, and for the presenters today for their time and efforts on providing this great information. Have a great day, everybody. Bye-bye.